It's a pleasure to have Adan Cabello here today to speak to us about graph-theoretic approach to quantum correlations.
It's a pleasure for me to be here, and today I'm going to talk about these two things. First, I will need as a tool this graph-theoretical approach to quantum correlations. We introduced Simone Severini and Andreas Mitter and myself long ago. And then the main topic today is to show that there's a fundamental principle for quantum correlations that we call the exclusivity principle. And these are the references I'm gonna touch. And the framework is a framework of general probabilistic theories in which I assume that preparations that yield the same probabilities for each of the available experiments are equivalent and define the same state. Experiments that yield the same statistics for all the states are equivalent and define the same test. And I will introduce this notation. I will call these pairs of tests and their corresponding outcomes. I will call them events. They are, whenever they occur with the same probability for each state, they are considered equivalent, and I will use this notation all the time. First here the test / outcomes. And I will consider that two events. For instance, here it means I measure X and get the outcome A, and here I measure Y, blah blah blah, set and get these outcomes are equivalent if the probabilities of these two events are equal for each state. And I will define two events as exclusive if they correspond to different subsets of outcomes of some test. Good. Everything starts, or an important part of this talk starts with this observation made long ago by Ernst Becker, which is a famous mathematician in Switzerland, in Zurich. He noticed in this small paper that both in classical and quantum theory, whenever there's one experiment that jointly measures observables A and B, another experiment that jointly measures observables B and C, and a third experiment that jointly measures observables A and C, there's always one experiment that jointly measures A, B, and C. We can summarize this saying pairwise commensurability implies joint commensurability. The point of this paper is that he noticed that there are logically consistent theories in which this is not true.
Okay, maybe you had it on the previous slide, you went through quickly. Precisely what do you mean by jointly measures?
Jointly measures that exist in the von Neumann sense. That exist A and B are jointly measurable if there exists a C such that the outcomes of A and B can be expressed as a function of the outcomes of this C. Okay, in that sense. Okay, in quantum mechanics, there's their commute.
Okay, they commute. Okay,
yeah.
Okay.
But for POBMs, this is already not true in quantum mechanics.
Yeah, as I said, projective measurements, and that's a good point. If you want to keep in mind, every time I mention the word test, I mean projective measurement in quantum mechanics. Good.
Or you mean there's a joint probability distribution, or such that okay.
A good key is that they are commuting, represented in quantum mechanics by commuting operators.
So joint measurability everywhere, every state.
Yeah, but
Yeah.
A and B and B and C can commute, but that doesn't mean A and C commute.
Exactly. But if this is the case, A, B, and C commute. Okay, that's exactly the observation of
okay. Oh, okay.
If A and B commute, B and C commute, and A and C commute, A, B, and C commute.
Okay.
Yeah.
So you can produce an experiment in which you can measure them together.
Okay.
That's the point. Good, but this is specific of quantum mechanics. Well, specific is it happens in quantum mechanics, but you can imagine universes in which it does not happen. Okay. Good. And we use this in this first paper with Simone and Andreas to define a class of general probabilistic theories satisfying what we call the exclusivity principle. Imagine you have three events that they are pairwise exclusive. Okay? Therefore, according to Specker, in this universe they are also jointly exclusive, or in quantum mechanics they are also jointly exclusive. Therefore, going back to Boole, the sum of the probabilities cannot be higher than 1. So, the principle states that the sum of the probabilities of any set of pairwise exclusive events cannot be higher than 1. That's the principle. Okay, good. Now, we are talking about correlations, for instance. The Bell correlations, the Closure-Simony-Holt scenario. You know it. We have a box in which we have two bottoms, A0 and A1, which is in Alice's hands with two possible outcomes, and the same second box here with two possible inputs and two possible outputs. So every time we pressure one here and one here, we have the corresponding outcomes, and we assume that we have, in the Bell Closure-Simony-Holt scenario, we have a space-like separation between the moment we press this and the outcome here, and the other way. And since we have this assumption, it makes no sense to say who was first. Okay? So we can do this. We can say that A0 is this button here, B0 is this button here, A1 is this 2, and B1 is this 3. So the Bell experiment is equivalent to this game in which you have a single box and you press two buttons, either this two, or this two, or this two, or this two. Okay? This is the notation for instance, for this event. Here I press bottom 0 and get this outcome 0, and here I press 3 and get 1. The first tool we introduce in this graph approach is a graph which contains all possible events in your scenario and their relations of exclusivity. Okay? And this is the corresponding graph. We call the exclusivity graph of the Closure-Simony-Holt scenario. Here, every event is represented by a node, and nodes in the same straight line or in the same circumference are exclusive, pairwise exclusive. Okay? This is as a definition. This is what we call the exclusivity graph of this scenario. There's another inequality we're going to pay a lot of attention to, which is the so-called Kleaschko inequality. This inequality is extremely important for two reasons. One is that it is the simplest inequality, classical inequality, non-contextuality inequality, violated by the simplest quantum system that violates a non-contextuality inequality, which is a three-level system, quantum system, acute root. You can, the same way you do with Bell inequalities, you can define polytopes of classical correlations, and the facets of these polytopes are the Bell inequalities. Here the facets are the non-contextuality inequalities. And if you look for the simplest physical system in which you have this, something beyond this classical polytope, you have to focus on the Q-treat. And if you ask, okay, what is the simplest facet in which you have a quantum violation, the answer is the Kleaschko inequality. That's one reason why this inequality is important. I will give you another reason soon.
So why was this only discovered in 2008?
Good question.
Nobody asked the question before?
Nobody asked the question before, yeah. Nobody cared. Nobody cared. For some reason, because it's not a Bell inequality, you don't kind of have, Alice and Bob. Okay. But in a sense, it's a kind of Bell inequality. It looks like this, and well, it's usually implemented in the lab this way. You have a source of spin 1 particles, you make a measurement, and then a second measurement will commute with the first one. You can do this with ions or even with photons. There are two experiments, one in Vienna and one in Stockholm, implementing looking for the quantum violation of this inequality. But for us, the point is the following. The Kleaschko inequality is equivalent to this game. It's a box with 5 instead of 4 buttons, and two possible outcomes. And the game is the same as before. You can press this two, this two, this two, this two, or this two. Okay? And again, you can construct the graph of exclusivity for this game, and this is the graph. Well, very nice. The next observation is that the correlations in any Bell or non-contextuality inequality can always be expressed as a positive linear combination of probabilities of events, as a sum of probabilities. Sometimes with some weight, but usually with all of them with the same weight. Okay? For instance, in the Cliasco is an example. And that is the second definition here, is the exclusivity graph, but the exclusivity graph now, not of the scenario, but the exclusivity graph of the inequality, meaning of the set of events explicitly appearing in the inequality. Okay? Basically, it's the same as before. Every vertex of the graph represents an event, and adjacent vertices represent pairwise exclusive events. Good. For instance, you have here the Cliasco inequality written as a sum, as a positive sum of probabilities of events, and of course the exclusivity graph of the inequality is a subgraph, in general a weighted subgraph of the exclusivity graph of the scenario. For instance, here we have just these black dots in the exclusivity graph of the inequality. So we can remove everything else and we have a pentagon. This is the exclusivity graph of the Cliasco inequality. Okay. Good. What about the closed-proportion manifold inequality? Well, you can rewrite the Bell inequality as a sum of 8 probabilities. Okay? And then, from here, you select these 8 vertices, which are these 8, and then you remove everything else, and eventually you look for a simpler isomorphic graph. So this is the graph of the closed-proportion manifold inequality. Good. One of the aims of this paper with Simone and Andreas was to understand quantum contextuality. By that we mean the quantum violation of these non-contextuality inequalities. Okay? And for that we wanted to sandwich quantum contextuality between two well-defined classes of contextuality. One obvious choice is the lower bound, which are non-contextual theories, classical non-contextual theories. Good. And for the upper bound, we decided to use these theories satisfying the E principle. Okay, I mentioned at the beginning. Good. And the first result of this paper is this. Given that S is a sum of probabilities, the operator in the inequality corresponding to a Bell or non-contextuality inequality, the maximum value of S for classical, and by classical I mean non-contextual hidden variable, or in some cases local hidden variable theories, quantum theory, and theories satisfying the E principle, but this is going to be important for the second part of the talk, the E principle that applied only to the graph S. I will give more details on this later. Okay? Well, the point is that these bounds are in one-to-one corresponding to well-known combinatorial numbers. The first is the independence number of the graph. The second is the lowest number, in this case the lowest number of the complement of the graph. Okay? Given a graph, the complement of the graph is the graph that has the same vertices, but every time you had an edge, you remove it, and every time you didn't have an edge, you add an edge. Okay? And finally, alpha star is the fractional packing number. So the funny thing is, okay, we collated these 3 physical bounds with 3 combinatorial numbers. That was fun. What is the independence number? Well, it's a maximum of these things, and the maximum is taken over all stable sets of vertices. And a stable set of vertices in a graph is a set of non-adjacent vertices. So if we are talking about a graph with weight 1, we're basically asking which is the largest set of non-adjacent vertices of that graph. That gives you the classical one. Okay? And it's easy to see why, because the classical one is always reached by a deterministic model in which you assign probability 1 to some of the events and 0 to the other. And since here the edges represent exclusivities, if you have probability 1 here and you have a connected vertex, then you have to have a probability 0. Okay? So the point, the maximum is attained when you assign the maximum number of probabilities 1s to the graph. Good. The second, the quantum upper bound, is a very interesting quantity which is called the Lobas number or the Lobas theta function of the complement. And is defined this way. It's the maximum taken over all orthonormal representations of the graph. And an orthonormal representation of a graph is one assignment of unit vectors to the vertices of the graph, such that whenever they are adjacent, the corresponding vectors are orthogonal. Well, in this case, we are talking orthogonal for the complement. Okay, so they are non-orthogonal. Okay. And, well, this psi is also a unit vector, which is called usually a handle. It's the initial quantum state for us, if you wish. And this maximum is taken over all possible dimensions, real dimensions. Okay. Good. The funny thing is that this is a well-known combinatorial number introduced for a well-known purpose. I will talk about it later. Long ago, that nobody before connected to quantum mechanics.
So sorry, I don't understand. So this is the maximum also of psi?
Opposite size, unit vector size. Yeah, basically this is the...
You take the maximum of psi and over the v dice.
Yes, exactly. But these should belong to an orthonormal representation of the graph. Okay, these v's are vectors that you assign to the vertices of the graph, and such that they are orthogonal whenever they are connected. They are adjacent. Okay.
Oh, so I was going to say the right-hand side doesn't depend on the graph, but it depends on it through the VIs?
Yes, but it's maximized over all of them. I mean, it's semi-definite programming at the very end.
Over all orthogonal representation also.
Yes.
So I guess my question is, how does the right-hand side depend on the graph?
Through the v's. The v's should be orthogonal representation vectors corresponding to the graph. Okay. Good. And finally,
I think you use a different version of the definition, right? Because this is not the original version of.
Oh yes, yeah. Well, that's one of the funny things. I count them long ago, and it was about 30 different definitions of the Lobas number. I decided to put this on purpose. This is the most closer to quantum mechanics things. But that's a very interesting fact by itself. There are many definitions of the Lobas.
There can only be one definition, and then you have terms that
Equivalent.
say...
Yeah, but let's, sorry. Equivalent. Yes, you're right. But I mean, coming from different fields, you get to the Lobas number from different arguments. That's my point. And well, the upper bound is this bound for theory satisfying the E principle, one copy, is also a well-known number which is called the fractional packing. and it's the maximum over all p's. Imagine that these w's are all of them 1, all p's, and for all clicks. A click in a graph is a set of adjacent vertices. Okay? So this clearly implements a restriction that the sum of the probabilities of pairwise exclusive events cannot be larger than 1. Basically, what you do here is you maximize the value of S with this restriction. That's all. But this has a specific number, name, which is this fractional packing. Actually, it's connected. Well, I mean, it was introduced by Claude Simon long ago. Good. Well, let's apply it. For instance, these are the well-known, in this language, the well-known bounds for the closure-Horst-Simony-Holm inequality. When you write down the closure-Horst-Simony-Holm inequality as a sum of 8 probabilities, the Bell classical bound is 3. The zeroth bound is 2 plus square root of 2, and the non-signaling bound is 4. Okay? When you applied this graph approach, you calculate the lowest number, the independent number of that graph I put, and you get 3. You calculate the lowest number and you get this, and you calculate the fractional packing and you get 4. Okay? And regarding the Kliashko inequality, these are the well-known bounds, 2, square root of 5, and for non-disturbance theories, which are basically no signaling, but no signaling between commuting observables, you have this thing, and when you apply the graph approach, you get exactly the same numbers. Good, very nice. You can use it to get, I mean, if you are interested in other inequalities, and you want to know what are the bounds, should you apply? For instance, this is the first application, non-trivial application of this tool, is for the odd cycle inequalities. Odd cycle inequalities are those represented by a graph, which is a cycle of with odd number of vertices. And by a graph, I mean the exclusivity graph of the inequality. For instance, this is an extension of the Kliashko inequality for an odd number. Okay. We have that in this paper. At the same time, Rob Speckens get a paper with exactly the same inequalities, but here we have the bounds using this nice approach. Good. But this is probably the most interesting result, which is that, in a sense, these graphs are physical, because for any graph you can imagine, there's always a physical system and non-contextuality inequality such that the quantum maximum is exactly the lowest of the complement of the graph. Moreover, the set of quantum probabilities is exactly one object that was introduced by Grotzel-Lowas and Schreiber, which is called the theta body of the graph, an also well-known conventional number. The theta body is defined this way. Basically, these are the probabilities such that V belongs to an orthonormal representation of the graph, and psi is the initial quantum state, in this context called the handle. Okay?
You take a maximum or take what?
All possible things. I mean, this is defined by all possible orthogonal representation of your graph. You have a graph, you have infinite orthogonal representation, and you expand this set of things. Okay?
Oh, so it's a set, right?
It's a set. Yeah, that's the point. It's a set.
It's a set.
The point is that there's a physical system in which you can go to the lab and expand exactly the same set. Okay? All depends on the minimum dimension in which you have what is called Lovat's optimum orthogonal representation. One that allows you to reach the Lovat's function, but by definition of the Lovat's function, there's always one. Okay? So there's always a physical system expanding this set. Good. Well, the way the inequality is constructed, there are many, but this is general. I mean, for any graph you can do this. You can associate, and for each event, for each vertex, sorry, now we started from the graph. For each vertex of the graph, an event, which is defined this way, in which this is the vector in the orthogonal representation corresponding to that vertex, and you assign answer yes to this vector and answer 0 to all the tests corresponding to vertices which are neighbors of the vertex you are interested in. Okay? This is well defined. You can check it in the lab, and defines a non-contextuality inequality and is violated up to the lowest number for some physical system. Good. Some comments. Well, computing the independence number is NP complete. And actually the lowest number was introduced both as an upper bound to the independence number and as an upper bound of the Shannon capacity of the graph, which is not even known to be computed. That was the original purpose of this 1979 paper by Laszlo Lovász. And in practical terms, the lowest number can be computed to any desired precision in polynomial time. Okay, good. But from this perspective of quantum correlations, this previous result identifies the lowest number as a fundamental physical limit for quantum correlations. Moreover, it identifies this theta body as the set of physical correlations for a given graph. Okay? So, an interesting question is why? Why, which principle makes these two quantities, these two objects, to represent natural correlations? A second comment is that this result is not true if we replace non-contextuality inequality by Bell inequality. The result said that for any graph, there's always a physical system and a non-contextuality inequality such that you reach the lowest. It's not true. If you put Bell inequality, for instance, you take the pentagon. Okay, you can prove that there's no Bell inequality reaching the square root of 5, which is the lowest function of the lowest number of the pentagon. Okay? And this is just a comment for people involved in the search for principles of quantum non-local correlations. It's just to notice that here we are kind of following a completely different strategy to the problem. I mean, we are focusing on graphs, not on specific physical scenarios. Typically, the problem is, okay, you have a Bell inequality scenario in which Alice have 3 settings with 2 outcomes, and both 3 settings with 2 outcomes. You construct the polytope, and you try to characterize the quantum set, and then you try to understand why nature has decided that this set should be the set. This, for instance, in the case I'm mentioning, can be an extremely difficult mathematical problem. But this problem we are addressing here is much simpler. You have a graph. Result 2 tells you that there's always a physical system for which you can expand these mathematical sets. Okay? And the point is to understand why these sets. So in a sense, you are free of extra constraints coming from scenario-dependent things. Okay? For instance, imagine a pentagon. You can have a pentagon representing a Bell inequality. But notice that whenever you have 2 events in the pentagon, 2 events representing a Bell inequality, the exclusivity is because the event in either side is exclusive, or because the event in both sides is exclusive, or because both are exclusive. And you need an extra restriction, which is basically, for that you need 2 graphs rather than 1 graph. Okay? The graph itself, a single graph, tells you nothing about Alice and Bob. And then it's very easy to calculate Lovász, since it's very easy to define the set. if you add extra restrictions, you are not in that simple problem. Okay. So this comment is saying basically that this is a relatively simple problem. Good. But then the idea was sandwiching quantum contextuality, and here this is the set of quantum, given a graph, the set of quantum correlations, which is this, is what I said before, is the theta body of the graph. What about the set of classical, and what about the set of correlations selected by exclusivity principle? Well, these are the definitions of the corresponding sets. Okay. But now the question is, what is the relationship? Well, in general, it's something like this. The classical set is a polytope. The E1 set is also a polytope. The quantum set is not. Okay. What else can we say about this? Well, this is the third result of the paper with Andreas and Simone, is that the classical and the quantum set are equal if and only if the graph has no odd holes or odd anti-holes as induced subgraphs.
So
Meaning a hole,
perfect.
this is a hole. A hole is a cycle of an odd number of vertices and larger or equal to 5. This is the set of holes. The anti-hole is the complement of a hole. This is standard names. These are the anti-holes. An induced graph, inside a graph is, okay, you remove the vertices and the corresponding edges, and what you get is an induced graph of the original subgraph of the original graph. So basically, what I'm saying is that if you give me a graph, and the question is whether this graph represents the exclusivity graph of a scenario in which we can have genuine quantum correlations, all I have to do is to check whether it contains pentagons, heptagons, or the complements as induced subgraphs. So if you give me a square, absolutely, there's no quantum interest in this thing. Moreover, the quantum set is equal to the exclusivity set for one copy if and only if G has no odd hole or odd anti-hole as in these subgraphs. So as before. And the third one is that G is a polytope if and only if G has no hole or anti-hole itself.
It's the same, right?
Yes! The same.
So why do you have to use this?
But it's if and only. I mean, this is all again. I mean, the funny thing is, from the physical perspective, comes first your question.
It's on the definition of a hole. So you.
A hole. A hole is a cycle with an odd number of vertices. A cycle is something like
Let's
this.
say, is it allowed that I have like a graph that has other edges around,
Yes.
but then there is a cycle inside?
It depends on the cycle inside. If the cycle inside is an induced graph, I mean, if you can get to this pentagon removing vertices and their corresponding edges, yes, you have a pentagon inside.
So, for example, it is allowed that my original graph, say for C11, that I have another vertex, say from 1 to...
Edge, you mean edge, from 1 to...
say I have an additional vertex to C7, I call it
Yes.
number 8, so I can connect 1 to 8 and then 8 to 6, and that's allowed.
Yeah, exactly. You remove 8 and then you have C7 again. But if you have C5, but in addition you have an edge connecting 1 to 5, you don't have C5. Okay? Good. Because, well, the proof. I mean, the proof is extremely simple because there's nothing to do, just check the literature. Because the classical set is exactly what is called the stable polytope of the graph, also called fractional vertex packing polytope or fractional clique polytope. There are many names in graph theory. Is it because the quantum set, as I said, is exactly there, theta 1? Is it because E1 is exactly the fractional stable polytope of G? And it is well known from here that this equals this if and only if G is perfect. This equals this if and only if G is perfect, and TH is a polytope if and only if G is perfect. And one of the most celebrated recent results in graph theory is the strong perfect graph theorem, saying that G is perfect if and only if G has no odd hole or odd anti-hole as induced graph. In other words, in graph theory, the graphs that are not interesting because they are classical, they represent classical correlations, are called perfect. And the graphs that are interesting for us because they represent genuine quantum correlations are imperfect. Imperfection is cool.
Do we have time to actually see what is the original definition of perfect graph?
No, we don't have time. I can show you that. I mean, everything goes back to Birch, and yeah.
No, the
I mean,
I will give you the details later.
can perfect be stated in terms of the adjacency matrix?
Yes, in principle the answer is yes, but the original idea was quite different. It was related to...
So it's easy, it's just the chromatic number of any induced subgraph is equal to the independent number of the complement, right?
Yeah.
So that's the definition of perfect. And this order whole thing just give a more transparent definition. So they are equivalent. This is the result of this strong perfect graph theory. So it's not so time, consuming anyway.
Okay. Yeah, actually, I had a question because, I mean, the dual graphs, in terms of the adjacency matrices, just replaces exchange zeros and ones, except possibly on the diagonal. Is there some convention about the diagonal?
Sorry?
To go from a graph to its dual.
Dual, you mean dual or complement?
Complement, I guess.
Complement.
You just exchange
yeah,
zeros
yeah.
and ones
Yep.
in the adjacency
Yeah,
matrices,
correct.
except possibly on the diagonal.
Yes.
Is there a convention about what you do on the diagonal, or does it not matter?
I mean, it's
Like just one, right? Or zero.
Or
is
zero,
not-
I mean, it's the same. Whatever your convention is, you don't change it. Okay, good. And then, okay, these are the three results of the original paper. Then let's go to the question of Popescu and Rolich, like that. Okay, why in quantum mechanics violates the Bell equality up to the Silverson bound, but not beyond the Silverson bound? What is the reason? It's not the no signalling, but what is the reason? Of course, nowadays we have many answers for that. Well, everything started with this, I think, with this work on non-trivial communication complexity. Is first by Wim van Dam, and then Gilles Grassard and other people worked on that and saw that if you accept this as a principle, the maximum you can get instead of 2.8 was 3.2, something like this. And in a sense, information causality, this paper by Marcin Pawlowski and others, is a kind of extension of this whole idea, and they get exactly the Silverson bound after a complicated protocol. Another possible way to get the Silverson bound is Miguel Navasquez and Harald Wunderlich called macroscopic locality, which is basically that if you lose the control on the individual particles, you lose the violation of the Bell inequality in quantum theory. But in other theories it might be different. But all theories satisfying this are satisfying this principle of microscopic locality. in a sense, recover the Simonson bound. And then we have other reasons, okay? However, if you follow the discussion of these issues, to what extent any of these principles is general enough to help us to understand quantum correlations? Well, to my knowledge, the state of the art is something like this. Information causality so far only singles out the maximum for quantum of quantum mechanics for closure Hall-Simony Hall, but not even the whole set of quantum correlations for closure Hall-Simony Hall, and it does not explain other experiments. Still open, but so far, to the best of my knowledge, this is the state. The same for microscopic locality, and this last option of the Heisenberg thing, yes. In a sense, if you assume quantum mechanics, you get quantum mechanics, is what Miguel Nosco is saying in this blog, on that paper, and in a sense, it's correct. In addition to that, there are more results saying that no principle based just on bipartite information can single out quantum local correlations, and to my knowledge, so far, no proposed multipartite principles singles out quantum local correlations. So, in a sense, the question is, what is the principle? If there's one singling out quantum correlations, it's an open question, fundamental question. Now, let's change a little bit the question. What if the challenge is, which principle singles out the maximum quantum contextuality defined as before? I mean, singles out the lowest number. Okay. As I mentioned before, this is a simpler problem, mathematically simpler problem. So maybe our chances to solve this problem are higher. And well, let's start with the simplest form of quantum contextuality. This is an old result, Specker, Bell, Cochin-Specker. The simplest physical system, as I said before, having quantum contextuality is a qubit. And I'm also surprised, like Frank, like until 2008, nobody asked the question, okay, what is the simplest inequality violated by qubit? Well, the Clash inequality. So for the Clash we can ask the Popescu-Roglic question, why square root of 5? And not the thing. Good. And this is the answer. Let's start with the exclusivity graph of the inequality. Remember, these are the events, and this is the notation, and exclusive events are adjusted. Okay? Good. How do you get a non-contextual limit? As I mentioned before, any classical limit is achieved by assigning probability 1 to some events. So if you assign probability 1 to this, these two should have probability 0. So the maximum number of greens you can draw in the pentagon is 2. That's explained the 2. Very nice. On the other hand, and this is curiously a very old paper, if you ask about the E1 limit, you allow any probability distribution with the only constraint that the sum of the probabilities of pairwise exclusive events is 1. And you ask, okay, what is the maximum? The maximum is 5 over 2, and it's achieved this way. It is in this old paper. Okay? And in between, we have quantum mechanics. Okay? So the goal is to understand why we have square root of 5. For that, consider 2 copies. As I mentioned before, there are 2 experiments testing the quantum violation of the Bell inequality. One is Seilinger's experiment in Vienna. There's another experiment in Stockholm. So imagine these 2 experiments running at the same time, independently, obviously on completely different physical systems. Independently prepare everyone in a pure state, no connection whatsoever. Okay? So here you have the events, the 5 events in Vienna, here the 5 events in Stockholm. And now consider global events, which are defined combining one event in Vienna and one event in Stockholm. For instance, this is a global event. The results of tests 3 and 4 in Vienna are 0 and 1. And the results of test 1 and 2 in Stockholm are 0 and 1. Okay? You can draw the graph, the exclusivity graph of these events. It's 25 events. This is the exclusivity graph. And actually, this graph is obtained using what is called the OR graph project. Okay. However, what is important is the following. Notice that here, you have several sets, in particular this one, of pairwise exclusive events. 5 pairwise exclusive events. Okay, so what? Well, the principle applied to any of these sets tells that the sum of these 5 probabilities cannot be higher than 1. But we are talking about independent experiments, so in principle, the joint probability of 2 independent events is just a product of the probabilities of each of them. So you have this value for the 5, and in quantum mechanics, if you substitute, hey, you get exactly 1. You already have 1. So imagine for a moment that you get, instead of a square root of 5, a violation of a square root of 5 plus epsilon. Then here you don't have, you have more than 1. You are violating the principle. So the principle applied to 2 copies of the experiment exactly singles out the maximum value in quantum mechanics. Good. But what about the Bell inequality? Well, in the next slide, there's what I think is the simplest proof of the non-existence of non-local boxes, if you assume the principle. Non-local boxes strongly violate the exclusivity principle. Why? Because, look, I changed the slide with the notation now. This is the probability that Alice obtains the result A for test X and Bob obtains the result B for test Y. But these are 5 events you have in a closed course inequality scenario. 5 events to which a Popescu-Roglic box assigned probability 1/2 to each of them. But this is also a pentagon. So if you take 2 copies, you are violating the principle. If you want to make more fun, you can do something else, which is you take 1 copy of this experiment and you get to Vienna and get 1 copy of the Kleasko experiment, which is also represented by a pentagon. You apply it, and you are ruling out non-local boxes. But now you want to recover the zero-sum bound, right? I have bad news, because we cannot calculate, when we do it with 2 copies, we don't recover the zero-sum bound. Actually, the conjecture is that the principle applied to an infinite number of copies singles out the zero-sum bound, but we cannot prove it. Because numerically we cannot go beyond 2 copies. The good news is that even with 2 copies, the upper bound you have, okay, is not 2.82, but it's 2.88 already, just 2 copies. Okay?
I mean, isn't zero-sum bound actually not 2 square root of 2, but Grothendieck's constant, which is...
There's a paper
But which is-
singleton, which connects the two things.
The two things, and then no one knows exactly what Grothendieck's constant is, and I think it's
That's-
bounded by 2 square root of 2.
Yes.
But this is, if you increase the number of observables, then you get Grothendieck's constant. Or in other words, this
Yeah,
2
yeah.
times square root of 2 is Grothendieck's constant if you impose a constraint on the number of observables.
Well, it's not Grothendieck's constant, but it's a correct bound number of observables
What's the correct bound for this problem?
for this problem.
Exactly, but here you consider a case where you have only 2 observables per site. Yeah? If you allow yourself to having an arbitrary number of observables per site, then you would have to replace 2 square root of 2 by Grothendieck's constant, which is, as you say, not exactly known. Yeah.
Okay, so that, okay. So this is-
Okay. This conjecture is, and actually this proof is in 2 recent papers. And what about this? What about other inequalities? For instance, previously I mentioned that every time you have a hole or anti-hole inside, you have quantumness. So in a sense, this hole or anti-holes represent a kind of basic quantum inequalities.
I'm confused, because, I mean, you just did all these things for pentagons.
Yes?
And yet you had this previous slide that said for pentagons, all of these different things were equal. There's something I didn't understand.
What else? I mean, so far I just argue about this experiment.
Yeah, but there was this theorem of several slides back where you said that if you had a subgraph that was a pentagon,
Then I have quantumness.
but didn't you have all of these theories equivalent? C of G was equal to Q of G equal to?
Yes, yes. If I don't have a pentagon or a hole or anti-hole, all the theories are equal.
Oh, if you don't have.
If I don't,
Okay.
sorry, if I don't.
Okay,
Okay, so-
okay.
So at the beginning, I said, okay, the Klearscu inequality is important for 2 reasons. One was mentioned. The other is, a reasonable question is, what is the simplest graph in which is quantum in this sense, in which you have a gap between the independence number and the levels? And the answer is the pentagon. What is this physical system represented by a pentagon? Klearscu. So also in this sense, Klearscu is a fundamental inequality. Okay? Actually, if you look carefully, the graph of the closure of Horst Himmelholt has 8 pentagons, 8 induced pentagons. That's why it's easy to prove this impossibility of non-local boxes, just looking for a pentagon. Okay, what else? Yeah, but what about other inequalities? Okay, I mean, does this trick works? I mean, can I recover the quantum bounds using the exclusivity principle applied to a number of copies? Well, first of all, do we have inequalities representing these situations? And I mentioned that from the graph perspective, interesting graphs are holes or anti-holes. Do we have inequalities represented by holes and anti-holes, meaning physical system violating these inequalities up to the lowest number of these inequalities? We already know that we have a family of inequalities represented by holes. There's also a family of inequalities represented by anti-holes. And what the E principle tells you about the maximum quantum violation in this case? Well, here, there's a strong evidence. I'm using the words that the mathematicians are, that the principle applied to an infinite number of copies singles out the maximum quantum value. This strong evidence to me is that in this case they can go up to 5 copies. And up to 5 copies, the first 3 digits are the same. This is what they wrote strong evidence. But it's nice. I mean, so again, it's an open question. It's, in a sense, it's related to the Shannon capacity of the heptagon. It's an open question. If you can prove that the Shannon capacity of the heptagon is exactly the lowest function of the heptagon, then you have proven that the E principle singles out both the heptagon and the complement of the heptagon, etc., etc. So, I mean, if somebody get this proof, please tell me immediately.
Can you repeat the question?
Yeah.
Yeah.
I mean,
No, just for pentagon. I mean, you mean just for Pentagon, you mean if the was is equal to what?
I mean, the point of the paper by Lobats is that he provides
Yeah.
the Shannon capacity of the pentagon. Okay? He
Yeah.
proves that it's equal to the Lobats, it's square root of 5.
Yeah, yeah.
Okay? While it's not known what is the Shannon capacity of the heptagon, or the complement of the heptagon. It's an open problem. Okay? Even the heptagon, nobody knows what is the Shannon capacity of the heptagon. But the Shannon capacity is defined as the n root of many copies of the independence number, in a sense. So it's connected to this. So basically what I was saying is that if somebody proves that the Shannon capacity of the heptagon is exactly equal to the Lobats number of the heptagon, which is what these papers are suggesting but not proving, then automatically you are proving that the exclusivity principle singles out the maximum quantum value both for the heptagon and the complement of the heptagon. Okay? This is my statement.
That one is only known for Pentagon, right? For others, I think they're not equal.
No, we don't know.
No. I mean, it's not no. What is true, no. There are different problems and it's important to separate. So far, I mean, everybody bets that is the case for the heptagon, that the Lobats equals Shannon. What is proven is that there are graphs for which the Lobats is not Shannon. There's a 27 graph which is a context sample for that.
No, I see.
But
No, yeah.
for this particular graph,
Yeah.
the E principle singles out quantum mechanics. So don't worry about that. Okay, so there are different problems. Don't make. Actually, our problem is in a sense simpler. All I was saying is that if somebody gets this big result in mathematics, automatically we have this very nice result in physics. But people are looking for years of this. Good. And then something which is more recent, which is Jan's observation. He proves the following. For any graph, the exclusivity principle applied to a composite system consisting of a target experiment represented by G, in the sense that G is the exclusivity graph of this target experiment, and a complementary experiment in Stockholm represented by the complement of G. And let me remark the fact that although the graphs are complementary, the physics is completely different, starting with the dimension of the physical system you need to make this completely different. Well, if you apply the principle to both things, then you can single out the maximum of G. But the big assumption here is that you have to assume that all quantum probability distribution for the complementary experiments are actually reached. You have to assume quantum mechanics in the complement. If you assume quantum mechanics in the complement, the principle will give you the maximum of quantum mechanics in the original graph. This is the result, which is very nice. Oopa. But you can do it better. If you assume quantum mechanics in the complement, quantum mechanics means you assume the whole set of quantum correlations for the complement, you can recover the whole set of quantum correlations in the target. Moreover, if your graph is self-complementary, like the pentagon, like many binary graphs, then the E principle, without any further assumptions, excludes any set of probability distributions strictly larger than the quantum set. For instance, I think this is a big result in the sense that all previous principles, like information causality, have this problem. You assume the quantum set, and then you say, okay, let's assume something else outside the quantum set. Can I rule out this something else? No. In general, no. The point is that here the answer is yes. Imagine you consider this, okay, what about this? Is it compatible with the principle? No way. what if it's closed? Is this compatible? No way. Okay? Good. So from this, I conclude that the principle seems to capture a fundamental limitation for nature correlations, since by itself singles out the set of quantum correlations in some scenarios, like pentagon or self-complementary graphs. There's also strong evidence that singles out the maximum quantum value for what I call basic quantum correlations, represented by holes and anti-holes, and also singles out the set of quantum correlations of any graph if you assume the set of quantum correlations for the complement. And if you give me 5 more minutes, I will add something else. Do you? That's another conclusion, which is the principle makes us to think about correlations in a completely different way. Because now we can learn about the correlations for one experiment, not by studying this experiment or copies of this experiment, but studying the correlations of a different, independent, and in principle, completely unrelated experiment. Let me put an example. Now you go to Stockholm and you test the Bell inequality. And on the other hand, you go to Rome and you test another inequality on a 5-dimensional quantum system, which is a non-contextuality inequality. It looks this way. I mean, we're talking about different things. Here is a sequential measurement of things, and the 5-dimensional is at least 2 qubits separate to things. Okay? In both experiments, you aim the maximum quantum violation of the inequality. These are the graphs representing the exclusivity of the events you test in inequality. The maximum is obtained when these probabilities are equal to this value. The maximum here is obtained when all these probabilities are equal. And then you do the OR product of these two graphs. And you start thinking in this graph. And you apply the in-principle to this beautiful graph, which is, okay, I mean, nature, whatever the principle that is governing nature should be consistent, right? It's an obvious thing. Okay, so when you examine correlations, you should think not about correlations here, but about correlations, any expansions, any extensions of your experiment can be produced, or a particular completely independent experiment. Well, this is not that bad, because notice here, inside this beautiful graph, you have actually 16 graphs like this, which are complete graphs on 8 vertices. Why? Well, simple, because these two graphs are complementary. You have this. So if you focus on one of these graphs and you write the, I call exclusivity inequality, you have this bound. I mean, the sum of these probabilities is bounded by 1. But again, the joint probability of 2 independent events is a product. And if you open the numbers, you notice that you already have 1 in quantum mechanics. So, I mean, this tells you that there's a completely different experiment than if you assume the principle and you do the experiment and you recover what quantum mechanics predicts about this experiment, you have an empirical proof that in this universe you cannot have higher than quantum violations of the Bell inequalities. Because a higher value obtained in Stockholm would violate the principle. And a higher value in the experiment in Rome would violate the principle. Even epsilon would violate the principle. So we did it. We went to Stockholm, we did the experiment. We went to Rome, we did the experiment. These are the data, extremely beautiful data. This is the graph. Well, these are the 16 inequalities. You expect here 1. These are experimental results. This is an experimental one. Okay? The conclusion is that, well, this is an empirical proof that no higher than quantum correlation satisfying the principle can occur. And these are the people involved in these experiments, and thank you.
Thanks very much. Any more quick questions? I guess we're over time anyhow, and any more discussion we can
I'm
have
here.
in Newton Institute for another week, yeah.
No, I'm here just until Saturday. I mean, I'm here tomorrow, basically.
Thanks, Aidan.
Thank you.
Oh, actually, Debbie,
Can you make the slides available to the institute?
Oh yes, there's no problem. Except for the part of the experiment, I have to ask the
Ah,
it's not submitted. It's not it's still, but everything else, yes. Everything else is submitted somewhere. Yeah, yeah, for sure.
okay, thanks.